Welcome, this is lecture number 51. In this lecture, we are going to talk about large signal controller tuning in boost as well as buck boost converter. So, here we will first recapitulate what we did for a buck converter, then we need to see the vector field and the geometric aspect in a boost converter, then large signal controller tuning in a boost converter and the tuning parameter summary boost as well as non-inverting buck boost converter. So, first if we recapitulate in our PID controller tuning in a buck converter, we have framed this into a PID controller problem where we talked about the switching surface takes the form of a PD controller and we can incorporate an integral action in order to reach steady state, almost zero steady state error, but we have discussed that it is the PD controller, primarily the proportional controller gain, which drive the the transient performance. That means, if we set it optimally, we will get close to time optimal solution. Okay, that part, analytical part, we have discussed in the previous lecture. In this lecture, we cannot fit in a PD controller in a boost converter because the voltage derivative in a boost converter is discontinuous, right? Because if you take a boost converter, for example, so we have discussed that PID controller for a buck, it was straightforward because in buck converter, if you see the capacitor current, if you see IC in continuous conduction mode, it is C dv0 dt in case of an ideal case. So, there is no problem, we can frame it into PID controller, but in a boost converter the capacitor current is discontinuous. When on time it is simply minus of load current and during off time it is IL minus I0. So, it is not like in the form of voltage. So, we will call it as a PI controller with current mode control rather than PID controller. But we want to see the large signal, we want to see the viewpoint. We have discussed multiple times about the vector field in lecture number 42, we have drawn how to draw using MATLAB 43, then we have also discussed the vector field in 45. So, here again we recollect that if we take the vector field, let us say these are the on state trajectory like a vector field of a boost converter, you see, and so depending upon the number of initial condition you can draw, and this represents our off state trajectory vector field, and we have already discussed how to draw such vector fields, right. Now, we want to, this is my initial condition, we want to reach this initial condition to our steady state point where the average inductor current is IL average and the average output voltage will be V rate, that is our steady state point. And under steady state it will have a on off operation because we need to have a switching frequency because it is a switching converter, right. So, if we take a surface, and we have already discussed about the switching surface, the red one indicate a switching surface which is a first order surface, and if we set the surface slope in such a way when the initial condition is start, the on state trajectory, this is the on state trajectory and this is the off state trajectory, this is our off state trajectory. It hit in such a way it reaches steady state point, right, and it is in one switching action it goes back to steady state, and these are the steady state switching operation, right. But how to get that? So, we want to relate first. Okay. The first point, again we are taking this switching surface, and this switching surface will show you it takes the form of a Kc into the current error, Kv into the voltage error, and since it is equal to 0, we can normalize it in terms of current error plus gain into voltage error equal to 0. And this you can get from this elements of power electronics book, that geometrical aspect. And here you will notice that in this method, these are the on state trajectory vector field, the green line. That means, this is the on state trajectory, and you see this trajectory and this trajectory, they are parallel, right. But it is not necessary this trajectory will parallel to this line. So, you have to take the close point and have to draw the vector field, that we have discussed. Once it hit this red, this is my red surface, the red trace indicate the surface which is sigma x equal to 0, and this is my sigma x, then it takes the off state trajectory, and the off state trajectory you will find that this off state trajectory, this is the off state trajectory, it is parallel to this path, and which is the off state vector field, the vector field of the off state trajectory. That means this is very consistent, and once it comes here, in this region they have a normal on off operation and with a very high switching frequency. That means the ripple is almost not visible, but it is actually going, and this concept is something similar to a sliding mode control that we have learned in lecture number 45. Now, since we discussed this, the surface we discussed, but the band, there has to be some band, otherwise your switching frequency will be extremely high, and that is practically not feasible. Your device will not operate, or it can even get damaged. We need to incorporate, this band. That means this is my sigma 1, this is sigma 2, and this one is my sigma. So around the sigma we will have a sigma 1, sigma 2, that is just a band, hysteresis band. Okay, and sigma 1 is sigma minus delta h by 2, sigma plus delta h by 2. So some band is inserted, so that once it reaches here, then it stays within this band, and this is something similar to your sliding motion. And you have to ensure that on an average this trajectory goes towards the desired point, where my output desired value is 5 volt and input current, I mean average inductor current is roughly around I think 18 or so. Okay. Now, what we discuss, we have taken this slope and we discussed this slope is minus Kp. That means if you take the slope here, the slope here is nothing but minus Kp. Now, this slope plays a significant role. You see, once it comes within the band, it takes a lot of time. So, it is like an overdamp response, and it takes multiple cycles to reach. And if you see the transient behavior, it comes here, then voltage here, it takes large number of cycles to actually come to 5 volt. So, this is something like a overdamp response, overdamp, or is like a fast order response. Because if you take the average trajectory, it is like an overdamp system, like a fast order response. But during this time, if you go back, this action we should not apply averaging, because this as well as this, there is a large time when you cannot do this on off operation, because it is driven by the off state trajectory. So, you do not have any choice. Similarly, on state trajectory, so you need to quickly come to this point, otherwise this can lead to very large overshoot undershoot. Okay. So, that is why the current overshoot is pretty high, and we can't do anything because this is an off state trajectory. So, that is one of the problems in a boost converter. When you want to start up the circuit, you have to be very careful about your startup process, because typically what people do, you need to slowly ramp up this VREF. That means some kind of a soft start. Otherwise, if you suddenly apply, then your trajectory will be forced to go like this, and you will end up with a huge, I would say, current overshoot. Because once you start this closed loop operation, if you slowly increase, that means generally if you take a time domain, in fact we discussed in I forgot the lecture number, the startup, soft startup. So, this is our typical VREF, our VREF desired, but actually in order to get startup for boost converter, we should raise the voltage like this and then keep it here. So, you need to put some kind of sleeve limit, so that this slowly increases, and this error, because your initial voltage is 0, it start, so it slowly start up. So, that we have to take into account, otherwise you will be bound to have such a large current transient, and which is unavoidable, and it can damage your switch, because it requires a huge rating of your devices to support such a high current overshoot due to the closed loop overshoot. But if you start raising the voltage like slowly kind of thing, because you may not get off operation because your voltage is starting from 0. So, it will like raise. So, you need to be very careful about the operation of the boost converter, right. So, because your reference voltage initially inductor voltage is high, but the output voltage is very low. So, you need to slowly rise. So, you need to consider a special startup circuit. So, that is very important for a boost converter. But in case of surface based design, we can always put a limit, but we may not avoid this path which can have a high current, because this direction is the current direction. Okay. So, that means we need to take care about the current limit in a boost converter in a way so that it will not exceed the device or the inductor limit, otherwise it will saturate the inductor. Now, imagine if we can increase this slope. So, what we did now, we have increased the slope. We have Kp is now, we have increased the slope. If we increase the slope, then you see it hit, current overshoot has increased, because if you go back to the previous slide, the current overshoot was around 22 ampere, not very high, but here it is around 30 ampere, it goes up to 30 ampere, this is my current, right. But interestingly, you see this is my on state trajectory, this is my on state trajectory, and this is my off state trajectory. And it goes and here it gets settled. That means, if you take the time domain, as if it start doing, it comes to the steady state immediately here, like here. So, here we have turn on, this is my on state and this is like our off state. So, that means during this whole process your switch changes its state in only once, and that is called the time optimal control. The fastest recovery is possible. But suppose if we increase the slope, so that means we get the right slope to get this time optimal recovery. If we increase the slope, then what will happen? Your current will hit this side and then come back towards your desired point, and this is how your output voltage initially goes higher than the expected value, and current overshoot also increases drastically. Earlier it was 30 ampere, now it is around 36-37 ampere, which is not acceptable. So, it is very important to select this line very carefully, otherwise it may saturate the inductor or it may damage your devices, and it can large voltage overshoot can also happen. So, that means to reach steady state from any initial condition, we can achieve this in one switching action. Yes, linear switching surface is enough, but we need to find the optimal gain that we have seen. Now, if we increase the slope that we have seen, the more current overshoot and voltage undershoot also increases, because even if you see the voltage undershoot here, it will also increase because your on time is large. So, in boost converter that is the problem. In boost converter, if your on time increases, the voltage also undershoot increases, because the voltage discharges this time, and that is not the case for buck converter. Okay, so that means your voltage undershoot increases, and very high slope your last signal, because if you take the slope, this slope minus Kp in such a way, this slope is become larger than this magnitude, larger than the on state trajectory, then system will collapse, it will go to the rejective region. Okay. So, but how to link this switching surface with the controller? So, we told that this is Kc into Kv, and if you separate out, it will be proportional control with load current feed forward. So, it turns out to be a current mode control with load current feed forward, where you need to set the proportional gain correctly. So, the objective here to find the optimal gain of the proportional controller to achieve time optimal recovery. Again, if you go to the previous lecture, where in buck converter we have discussed, we need to also incorporate an integral action, because that will ensure almost zero steady state error, and that integral action will happen slowly, it will have negligible impact in the large signal recovery. So, we can design the integral controller just by using small signal model, but we need to find the proportional gain using large signal model. So, if you choose a larger gain, you will get more overshoot, and that we have discussed. So, you have to be careful about the optimal recovery. If you derive this optimal recovery, that means this was our initial steady state behavior before the load transient step takes place, and this is after load transient. Interestingly, the average inductor current in a boost converter, that means your average inductor current is nothing but Vref into y V in into load current. So, here this we call it as a normalization factor into I0. So, that means any step change in the load current will appear like a normalization factor in the step change. That means the step change in the inductor current that needs to go, that means we need to change this inductor average value, which will be Kn normalization time into the load step size. And now we need to get the optimal slope, and which is minus Kp. That is my problem, my objective. So, this is my on state trajectory, this is my off state trajectory, and you can derive the same thing for the step down also. We have discussed the IN average is a normalized current, load current is nothing but your average inductor current. So, now if we write the switching surface equation and if we incorporate integral gain, and I told you the integral gain we do not consider during a large signal recovery, because this effect will only come during steady state and it has no influence, only it will shift the offset point to its desired, that means it will shift the output voltage to the desired Vref, that is the function. So, during the large signal recovery we will not consider the integral action. Now, again if we write like a buck converter, here you see the Q1, Q is equal to 1 when S is on, and it is 0 when S is off, that means switch off. So, here Q bar is nothing but 1 minus Q, okay, and here also we have a Q bar. So, you can write this state space equation dx1 dt, you can obtain dx2 dt, and we have written here this whole thing we represented by Q bar, this will be represented by Q bar, okay. So, this is in this paper we have derived in detail, it is available. So, again if you write dx1, if you write dx1 by dx2, you will get this expression. Now, you need to solve this by means of integration, because it is just a, you have to solve this equation. But we are not going to show each and every derivation step in the boost converter, because the derivation is quite cumbersome, it is complex. Rather, we want to just show the step. So, this is the solution that we can obtain, where Q we have to decide whether we are talking about on state trajectory or the off state trajectory. For on state, we have to take Q equal to 1 for the on state trajectory, and it is equal to 0 for off state trajectory. So, on state and off state trajectory are simply nothing but by changing the Q value from 1 to 0. Otherwise, this equation is applicable for both the trajectory, only you have to check, you have to substitute the suitable Q value. Now, here it is V1 I1, because this is a point and where V0 is my x axis and IL in the y axis. So, our initial operating point is here. So, where we need to substitute here, that means if we take this to be our initial average inductor current and this to be our final average inductor current, and this is the average current change which is a function of load step size into the normalized factor, right. Then we can find out I1, and this equation is simple because it is a straight line equation, because if you go back, if you substitute Q equal to 1, this term will vanish, this term will vanish. So, it will just solution of one first order equation, it will look like a first order, because it is like a line, it will not pass through origin, but with a negative slope. But the off state trajectory equation will be somewhat complex, that is why we are not deriving full. So, we can write V1 I1 is the final condition for on state, and V1 I1 is the initial condition for the off state, and the final state is Vref Iref2 and this is Vref Iref1. I ref 1 is the reference current before transient, I ref 2 is the reference current after transient. If you substitute and solve it, you will get an approximate. Original equation is quite complex, but the approximate, because there are some term which has almost negligible impact. But if you separate out the actual term which are dominating, you will get the approximate relationship this, and this is nothing but our 1 by Zc square, the characteristic impedance square, and input by output. So, you will see you need to know the load current, duty ratio, anyway you can get it. If you do digital control, you can get the on state off state, but else we are assuming it is known reasonably, it does not vary too much, but here you need to get the information of input voltage and load current. So, the input voltage we can access because it is a voltage. If you go to any commercial IC, we can have a provision for input voltage sensing, but the load current sensing is the difficult task. We generally do not go for actual sensing of load current, though for boost converter the load current is somewhat lower, because if you are going for high voltage low current application, but still it is not very much recommended, but we can use an estimated load current algorithm. Suppose we did it for, if you go for LED driver, then again the load current can be obtained by, because in LED driving we have to go for PWM dimming, where the actual nominal current we know it, and when we are going to turn on and off, that signal is also generated from our controller. So, by taking the status of the signal, we will know the load step size, because we know the nominal current. It is possible. And of step down transient, it is simply C by L, V by I0. So, we can summarize this step, but we are not going to go into the actual derivation, because as I said, the expressions is somewhat complex. So, that is why we avoid here. Similarly, for non-inverting buck boost also we have derived, but this derivation is quite complex, but we got the simplified expression with the proportional gain, where duty ratio we know, we can find out input voltage if we sense, but we need to know the load current information, where all this information can be obtained otherwise, because input voltage we can have an arrangement for sensing, but load current either have to estimate, then we can plug in this into lookup table. But how do you change it? So, we can compute or we can create a lookup table, because we have discussed about gain scheduling. So, such gain scheduling can be incorporated in large signal tuning, where we can get the parameter value for a certain loads condition or input voltage condition. Otherwise, we can do computation, because that is not a very complex term, we can do it in our digital controller platform. So, this is also discussed in this paper. So, we can go for this our tuning, large signal tuning method for buck boost, as well as this was extended for cascaded DC-DC converter, and that will see show you in experimental result, maybe in the last week we will show you. That was also applied, and it is not very difficult, it is also simple. So, this tuning method can be applied for buck boost, two-stage cascaded converter, even if the cascade has a buck and boost, or two buck, two boost. So, we can extend this technique. Only thing we need to have a load current information, either if you do not sense, by some means of estimation. So, with this I summarize that we have recapitulated the controller tuning in a buck converter, then we draw vector field and geometric aspect in a boost converter, then we talked about large signal controller tuning in a boost converter, and then we have summarized the formulation of the tuning parameters for boost and non-inverting buck boost converter. So, with this I will finish it here, and we will discuss the MATLAB simulation case study in the last week. So, with this I finish it here. Thank you very much.